Morning, everyone.
Good morning.
Morning.
I do have it. Awesome. All right, I got to show you something new today. It's not new, but it's another way of doing something that gets us out of a pickle, and I'll show you when we get there. I want to do a quick intro, though. Something that didn't make a lot of sense to me when I was learning all this because it was a little too mechanical was just the fact that don't forget what you're really doing here. This is one that I think is really kind of cool. Let's see. So this is something I do quite a bit. So let me see if I can find this page. Getting close. So drawing house plans, I'm speccing out beams like these a lot. These are called Versalam beams. You future engineers will understand this a lot later. I just want to show you something kind of neat about this. So these beams here, I just want to show you one thing on this that maybe doesn't make a lot of sense, but let's just stare at these beams for a second. Let's look at this one. This is a common one I spec out here, which is a 3.5 inch by 9.5 inch. So it's 3.5 inches wide, 9.5 inches tall. But then let's go read the specs on it. It says it weighs 8 pounds per foot. And then it says it has allowable shear of 6,300 pounds, which basically means the beam won't rip in half vertically. It's 6,300 pounds. And then it has an allowable moment of 13,958 pounds, which basically means it won't break in half when you put weight on it. And I want to show you how. That's a calculus problem, or that's a calculus statement. So we'll come back to that in a second, after I show you how to calculate that.
Well, wouldn't the foot over pounds be kind of indicative of that being a calculus thing?
Very well said. Very well said. Moment is torque, and I'll show you kind of how this works. Just interesting. So if you have a beam that's under load, it's going to do that. It's going to bow down. And at some point, it's just going to break. And it'll probably break in the middle if everything is kind of normal. But basically that whole beam, if you think about just kind of the left half of it past the crack over there, this part over here, that whole part of the beam wants to rotate downwards. And basically it's trying to split the beam apart in the middle. That's called moment or torque. And torque is force times lever arm distance. So what happens is on a beam, there's a certain amount of weight that is in pounds per foot, which, as you pointed out, Justin, is kind of a calculus statement. And let's put, I don't know, let me think here for a second, let's kind of make it big. I don't know, 712 pounds per foot. Is that big? Let me think for a second. 50, that's not that big. Let's make it 900. So 912 pounds, roughly 1,000 pounds in every foot of that beam. And so what we have to do is think about how badly does that want to rotate. Again, what I'm interested here in, and it says integrals, but it's not related particularly to what we're doing today. It's just that, well, that's a per pound per foot. And let's say that this thing is, and L is the length in feet. Let's give this thing a 24-foot length. So this thing is 24 feet long. And so that means there's 12 feet over here. And does it make sense there's weight continuously across the top of this beam? There isn't just 912 pounds. It's not just as simple as 912 pounds here and then move a foot, 912 pounds there and then move a foot. If you think about it, wouldn't it be more like, okay, well, that is true. That's an approximation, 912 pounds every foot. But there's also weight between there. In other words, if I cut 912 in half, what is that, 456? It'd be like 456 here, 456 there, 456 there. Now it's like 456 every 6 inches. And then you could even cut that in half and go every 3 inches. Half of 456 is like 275 or something, 278. But the point is it's actually solid full of arrows. And the way torque works is it's a force times a distance. So for instance, this one right here, just to keep it simple, if that's 912 pounds, that'd be a distance of 12 feet. So 912 pounds times 12 feet is whatever, 10,000 pounds. 10,000 foot-pounds of desire to rotate. That's what torque or moment means, is desire to rotate. But then wouldn't we have another 912 pounds, except for it would be at 11 feet. And then another 912 at 10. But again, as I said, it's even really worse than that because there's arrows in between all of those. So what I want to do is quickly develop the calculus or the algebra formula that engineers use. And when I saw this, I actually called some engineers and said, where does this come from? And they didn't know because they were just given this formula that I'm about to give you. I'm about to make for you using calculus. And that's why they didn't know, because it's a kind of a calculus idea. And you're not using that on an everyday basis. So let's make the formula. So this whole thing is a distance, the whole beam is a distance of L feet. And we're going to put W right here. So there's 912 pounds right there. But does it make sense we want that to move everywhere along that 0 to 12 feet? So what we're going to do is take a tiny little slice of this. This is what integration really is. It's adding up lots of little things. So if we take that weight, remember how a second ago we said that weight was 912, and then we said, well, what if it was only 6 inches and not a foot? Well, then that would cut it in half. And so I'm going to say the distance to wherever that slice is X, which means the thickness of that is a tiny amount of X. So if we take the weight times the tiny amount of X, that's our weight. So 912 pounds a foot. If we only wanted that to be 1 inch, like we wanted to add up lots of these, if we only wanted it to be 1 inch, 912 divided by a 12th, that'd be 76 pounds. It'd be 76 pounds on that inch, and then 76 pounds on the next inch, and 76 pounds on the next inch. So this is basically your force, your weight, your total weight. And so torque is force times a distance. Well, there's our distance. Our distance is X. So it's a force times a distance. And now all I have to do using calculus is add all of those up. And I'll write it maybe the way you're used to seeing it, where the dx is at the end. I need to add all of those torques up. while x works its way from the middle here all the way to 0. Well, the middle is half of the distance, whatever that distance is. We were treating it like 24 a minute ago, but we're going to try to make a formula for everything. So all the way from there to 0. So we're adding up millions of little tiny torques. Instead of just having 12 912-pound kids sitting on that 12-foot section of beam, we're going to have millions of them. This is what integration does. Notice this is not area under a curve. Integration is adding up lots of little things. Well, the W is just a constant, 912, whereas the X, however, is not. X is going to vary because we need X to be everything from half the length to 0. Well, you should know how to take the integral of that. The integral of that would take that x and raise it to the second power and divide by 2. And then I'm evaluating that at L over 2 and at 0 and subtracting. If you put L over 2 in there being squared, you end up with L squared over 4 over 2, or L squared over 8. This is the formula those engineers knew, but they did not know where it came from as a shortcut. So engineers are not using integration on a daily basis because somebody's made an algebra formula. So this is the moment formula. And these are the specs for it. So now let's figure that out. So we have this beam that we say, okay, great, let's use this formula. Well, we put 912 pounds per foot in there times the length of 24, which is squared, divide by 8. Let's see what we get. And I was just guessing to see if this came out okay. 912 times 24 squared equals, divided by 8. I got, ooh, that's big, 65,664 foot-pounds. What that means is my beam is going to have a lot of desire to rotate. It has 65,000 foot-pounds of desire to rotate downward. Does it make sense? That wants to rip the center of the beam apart. And so that's what was on that chart a minute ago. So remember that 65,000 number. Let's go back to that chart. Hopefully there's even a beam that's this big. There may not be. So let's go back to the beam I was looking at, 3.5 by 9.5. See how it has a 13,000 allowable moment? Well, ours was 65,000, like 5 times that big. So if we put this beam in there, it's not going to handle it. Basically, it's saying it will handle it if it's up to 13,000 foot-pounds of moment, but we're putting 65 on it. Is there even a beam in this that's that big? So there's 4,600, 56, that's getting close. Are we up to 65? There's one, 70,000. There's our first beam. This is what engineers do. This is our first beam that would work. What is it? It's 5.25 wide by 18 inches tall. So in order to carry the weight that I just needed for that house, I'm going to have to choose that beam. Or notice there's some other ones. You can choose a beam that's plenty stronger than that. But that's an example of kind of what integration really is. It's adding up lots of stuff. I don't know if I went too fast I obviously don't have time for you to completely understand that, nor do I really want to. But it's just that when you sit in a calculus class, you tend to just do calculus book problems. And, if you're honest, you say, well, when am I ever going to spin some weird, stupid shape around the y-axis? As neat as that is, it's kind of cool that you can find that volume. But I just need you to understand that, that's what integrals really do. They add up lots of little things. And that is not always just the area under a curve. And secondly, that formula that I just made, that's what engineers use. They're not doing calculus on a daily basis. Calculus is what gave us that formula. But on a daily basis, we just have an algebra formula. And that's what we've been doing the last couple of days. Like we found the volume of a cone yesterday as an algebra formula. And now you're in a spot where you say, hey, I actually understand where that came from. I can make that formula for myself. Cool. Okay. So now we're going to look at something called a different method called shells, and it's doing the same thing. But let me show you, let me see if you can answer this question. If I gave you this shape right here, so this is kind of a little bit of a warm-up, an intro. This is just a geometry problem. It's not a calculus problem. If I gave you this shape right here, think of this as kind of just a piece of pipe. It's hollow. How would you find the volume of the pipe itself? Not the volume of the water that goes in the pipe, but just the pipe itself. What are you going to do to find that, given that it's hollow? You really got a couple of ways that you might do it. You tell me.
You could try submerging it in water.
Yes. Remember, you can take anything, even something as weird shaped as this eraser, and just drop it in the water and measure how much it comes up on the kind of on the beaker, and you would know exactly. And that's totally true. What if you, as we're going to do today, did it based on its measurements? What if you knew this thing was, I don't know, 6 inches tall, and you knew that it was, let's see, I'll try to make this proportionate, say 2 inches wide. But I actually want to know the volume of, say, the copper that the pipe is made out of, or the plastic the pipe is made out of, or the concrete.
Would you know the thickness of the walls?
Good job. Does it make sense that the dimensions I just gave you would allow you to know the volume of the cylinder, but you got to know how thick the walls are too. And so let's add that to this. Let's say these walls are 0.1 inches thick. So that's that distance right there. What do you do? How are you going to find that? There's more than one way, but how would you find it?
Can you take the volume of 2 cylinders and then just subtract the smaller cylinder from the larger one?
That's exactly right. You could take the outer cylinder, find its volume, take the inner cylinder, find its volume, subtract them. You found it. Excellent. What's another way? And that way works fantastic. But I'm gonna show you a way that will make our life a little easier today. What happens if I chop this right there and laid it open? What would I have?
Rectangle?
Yeah, wouldn't it just be a rectangular box?
Well, almost one, I think.
Say that again. Almost. Say it again.
Well, it would have almost a rectangle. It wouldn't be perfectly one, I don't think.
Yeah, and you're saying that basically because if you know, the distance around the inside, if you will, is not the same as the distance around the outside. So there is a bit of a technicality there that we'll talk about in a minute. But does it make sense if you chop that and unrolled it? Think of it as like a noodle or something that would want to open, whereas like a plastic pipe would not want to do that. Does it make sense this distance right here would still be 6 inches, and that thickness right there would still be 0.1 inches. The only hard thing is, how long is this distance down here?
Half the circumference of what you measured, the outside.
That's exactly right. Isn't that the circumference of that measurement of that sort of circular top? So this is really the circumference of the original shape right here. Remember that formula is 2 times pi times radius. So in our case up there, the diameter was 2 inches, and so the radius would be 1. The other formula for that sometimes is just pi times diameter. Maybe you've seen that. Pi times diameter. So for us, this is going to be 2 times pi. And then all I need to do is multiply all 3 of those things together. Wouldn't that also give us the volume? So I'm going to do that. 0.1 times 6 times 2 times pi. I got approximately 3.77. 3.77, that'd be cubic inches, because it's inches times inches times inches. So both of those would work. What we're doing today is something called cylindrical shells, and it's going to be filling these spaces using this shell that I just described, not a washer. And I'll show you why in just a second.
One thing, it looks like you said that the thickness of this tube is an inch. Is that what it says?
0.1.
Oh, 0.1. Okay, because I was like wondering if that makes any sense.
Yeah, it'd be too fat. So yeah, 0.1 inches. So it's really thin. Now, of course, you can tell where this is going. For us, that 0.1 inches is going to be infinitely thin, which will take away the problem that I heard one of you say, that it's like, well, you know, if you opened it, this length here is much shorter than that outer length. And so when you lay it open, you know, is that just a rectangle? Well, it only would be if the wall of that was really thin. Think piece of paper. You know, I've got this piece of paper right here. Hey, look, it's a rectangle. It still has thickness to it, very, very small thickness, but can't I roll it into a cylinder? That's what we're going to do today. So if I open that up, yeah, it's just a box. That's what we're going to do. Because it's infinitely thin, you know, this is not infinitely thin, but it's really thin enough that I'm not going to have the problem I had with this picture.
But if you found the volume of that rectangle cube, wouldn't that just be the volume of the rectangle and not the actual cylinder?
That's correct. In other words, we are thinking of this as being hollow. So you found the material that it took to make that, if you will. It's empty on the inside. It's not full. Now I'll show you what I mean in just a second. I'll show you where
Okay.
it's in play. Let's do that. Let's do that now. So let's see. Let me turn some stuff off here. Ding, 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 ding. Too many things off. So let's consider this shape right here. We've been playing with shapes like that. We've been rotating them around. Are you good at time? Do we take the time to do this? I think you're good at this. If I send it around in this direction, if we took that shape and we rotated around the x-axis, you can do that right now. I'm going to just quickly draw a picture of that. So what we've been calling the washer method works fine in this instance. And so it kind of helps to, you know, have a drawing like the drawing I just made just to stare at. And you may have noticed I also kind of drew the image of it down below. So what you're really doing when you make washers out of this is, well, you're first, let's see, you got to do this correctly. You're picking a spot, say right here. And you're saying, I'm going to go around that shape. I'm going to consider that shape as, well, that's just a disc. So that's a cylinder, right? So if I just move those cylinders this way, and notice when I move them to the left, the cylinders are getting smaller, right? When I move them to the right, those cylinders are getting bigger. That's why we need an integral, because we're going to have to add up a lot of those cylinders, and they're changing size all the time. And it's the blue line that's changing their size. And so that's why I got to cruise along that blue line. Now, in our case, we're saying, hey, I want to rotate this shape around the x-axis, and so I'm getting kind of this cool cone-ish sort of a shape. Notice it is a cone. It just has a kind of a weird kind of rounded out, hollowed out inside. I don't know how well you're able to picture that. So if I want to find the volume of that isn't just a truncated cone. I'm coming back and actually subtracting off something on the inside. And so again, I'm very interested that you just see, hey, look, those cylinders are sliding up and down in that cone, and I just have to find the sum of all of them added together. And if I want to get this right, they got to be infinitely thin. Except we're coming back and saying, well, unfortunately, they're hollow. So there's this hole out of the inside. So that's why we're calling them washers, right? So what I hope you're good at now is saying, okay, so what am I really doing to visualize this? I'm saying, well, the radius of that one, since that's kind of the line, the radius of that line right there, that's the height of that one. So to find the volume, I'm going to say pi times the radius squared times the height. And in our case, that height would be a little bit of x, right? So that would be the sum of all of the, well, disks. But then I'm coming back and saying, yeah, but we also have to consider this inner radius, which is the radius of the parabola. And I got to subtract that off. I got to subtract off that cylinder. So I'm subtracting off pi times the radius of the parabola squared times dx. And I'm just adding those all up. Do you see that as what we're really doing? And in the end, those radiuses are really the y coordinates. And so maybe I'll just switch those out. That's the y coordinate that we're talking about there, since it's going up. And this is the y coordinate of the line. So that's what all of our problems kind of looked like, because we were able to slide a washer all through the shape. And so since we're sitting here working with x's, since we're stuck with, in a sense, I say stuck in quotes, we're sort of stuck with dx, then all you're doing is saying, hey, cool, this line down here tells me that y equals 2x plus 4. So then I can just replace that y with 2x plus 4, and I'm on my way. And I can replace the other y with what it is. Y is x squared minus 6 plus 11 for that parabola. I replace that over here. And then, hey, look, I have all x's. And then I look at the graph and I say, hey, that's just working its way from x is 7 to 1. So I'm going to add up all of those washers as x slides from 1 to 7. That's what we've been doing. So hard to visualize. Now, what we want to do this time, however, that is not going to work very good is this. I want to take that same exact shape and spin it around the y-axis. Why is that not going to work very good in this particular case? Can anybody see why that isn't going to work very good?
Because all your equations are set to spin around the x-axis.
Yeah, the equations are really nice kind of around the x-axis. Let me show you what I mean. Let's see here. Did that work? I don't know. I don't think that picture took for some reason. User error. I'm going to sketch on this just kind of ugly style. And then we'll go back and kind of do it nicely. I just want you to be convinced this isn't going to work. And because I wouldn't think you're convinced of that yet. So you should say, well, what's the problem? I don't get what the issue is. It's no different. Let's go black. It's no different. If I go right there and right there, we're talking about a disk that, where are you trying to make a line? I do not know. Weren't we just talking about that disc on the outside? Like, what's different? Nothing's different. This is the same. Nothing's wrong here, except for in this particular location, we are subtracting out that hole. Why is this any different? It's not. I mean, isn't this the x coordinate of the parabola? That's the radius of the larger one. And isn't the radius of the smaller one the x coordinate of the line? Like, why can't I just do that? Anybody see the problem with this? Like the picture I drew, there is nothing wrong with it. But where?
Well, this one is probably fine, but once you get to the bottom of the curve, I think it would probably be kind of difficult to do anything.
Yeah, do you see what happens when you're down here? When you slide it down here, do you see what's going wrong down here? What do you notice about the inner circle now that we're subtracting?
There is no inner circle.
Yeah, it's like it's not hitting the line anymore. Does that make sense? What I want to say is, with respect to left and right, the parabola is not always above the line. When I get down to where I am right now for the first time, suddenly, the inner shape is actually stopping on the parabola. So does it make sense down here? It's the first one is fine. It's the x coordinate of the parabola. That's the radius, but the inner radius is now also the x coordinate of the parabola. Does it make sense that we're not in the line anymore? You see the problem with that? This doesn't work. Again, I've been giving you problems where that we were sort of careful that that didn't happen. Did you notice up here, if you will, the line was always above the parabola? So it was always, in my equation up here, sort of blue minus red. That always worked. The outer radius was the line, the inner radius was always the parabola. But because this parabola has kind of a dip in the bottom of it, then that isn't going to work. And so this is what shells is going to allow us to do. Again, it's a pretty brilliant idea. So let's see if we can get shells to answer this. So what I'm going to do is just draw a different shape in there. I'm going to draw in those cylindrical shells that we just did kind of a quick practice on a second ago. So what would that look like? Sometimes abbreviated shells, but it should be, at least in your mind, called cylindrical shells. So let's see if we can pull this off. So what I'm going to do instead, and by the way, the other thing that's really tough about this method right here is if you're going to take, there's a thing that's even worse. If you're going to take this equation right here, since your thickness in this is a little bit of y and you need to work in y, what are you going to have to do with this equation to be able to plug in something for that radius right there?
You're going to have to take the square root of y.
Yeah, you're going to have to solve this for x. And we did that before, but this problem has not only y equals x squared, but it also has a 6x. Can you appreciate that's not going to be easy to solve for x? And if this was a cubed equation, it would actually be impossible to solve for x. That's another problem with this method. So the fact that this is forcing us to work with y because its thickness is dy makes the equation that we're given over here, lots of times equations are solved for y when we're given them, not solved for x. And so we have to be able to solve it for x. Really, we can't in this case. And you can still using the quadratic formula. It's just really ugly. Cylindrical shells actually makes this fairly easy. So we're going to fill this up in a totally different way this time. This is what's so cool about it. So we're going to take let's just take a spot here, right here. I'm going to try to draw this in such a way that you can see it okay.
Yeah, you were saying you could have solved it with the quadratic formula, correct?
Yep.
But it was just be messy. Yeah, I was thinking that same thing when I was looking at it. I was like, well, I mean, like technically you could find the quadratic thing of each x value and subtract one from the other, but that sounds like a lot of extra work.
Yeah, and that's because this problem is that's probably because this was a nice one. Like, what if I made an x cubed equation, or what if it was y equals the sine of natural log of x? Like, there's lots of equations you cannot solve for x. You can't. This one's hard but doable.
Right.
We're going to do
That
instead
makes total sense.
is, this is what's brilliant about this idea. We're going to make this cylinder here and this is the cylinder that we did at the start of class. Does it make sense? I can slide the side of that cylinder to the right, and then it'll go up here to the top, and it'll be like a, I'll erase this one, but it'll be like a super long and skinny one when we get up there at the top. But I can slide that to the right, and it's going to get shorter and wider as I slide it to the top. And I can also slide it to the left, and this will slide all the way through the shape. And the whole time, the height of that will be blue minus orange. Let me show you what I mean. So this thickness right here, because it's horizontal, is a little bit of x. That means we're going to work with x's. That means that this equation over here, we're going to like it just like it is. Cool. Well, would you agree that this distance right here, where our cylindrical shell is located right now, that's its radius? Isn't that just the x coordinate that we're at right now? In other words, wherever you happen to be on this graph, whatever x you happen to pick, notice we're going to be working our way from x's that are from 7 to 1. So x will be everything from 7 to 1. And so this radius is really just x. So remember, to get the volume a minute ago of that shell, we had to know the height. We had to know the radius so that we could plug it into this circumference formula, because that was the distance around it. And then we had to know how thick it was. So in our problem, we know how thick it is. That's dx. We know its radius is an x. And then all we have to do is get the height. What's the height over here? What's the height right over here? How tall? How do I figure out how tall that is?
Subtract one function from the other.
Yeah, isn't this height right here, the blue height, isn't that the y coordinate of the line? And that orange one, isn't that the y coordinate of the parabola? So isn't my height then going to be the difference between those two, as I think Justin just said? So my height is going to be y line minus y of the parabola, which is the same thing we did before. That's my height. So the unrolled box volume, isn't that dx, the thickness, times the circumference times the height? So that'd be dx times the circumference, which is 2 times pi times radius, times the height, which for us is y of the line minus y of the parabola. And since r is just x, I could say dx times 2 pi x times y line minus y parabola. Keep doing that. And I just need to add those all up. Again, if you're kind of a formula person, you probably would find this formula in the book. Since in this case, we're going around the x-axis, then the integral will be 2 pi x times y minus y. As far as the formula in the book, it's going to be like the y of the top minus the y of the bottom or something like that. TB, top, bottom, dx. Does it make sense? That's kind of the generic formula for us, where this is the height, this is the thickness, and this is the circumference. So you probably see some formula that looks something like that in your book. Let's try that out with this problem then. So for us, since we're working in x's, I need everything to be in x's, and this shell is sliding from x is 1 to x is 7, and 2 times pi times x, I don't need to mess with that. And now I just have to replace y of the line. The y of the line was right here, 2x plus 4. So the line was taller, so that's the 2x plus 4, minus the parabola. The parabola's y value was x squared minus 6x plus 11. So it's really those two subtracted, and then there's a dx out there. How's your brain? Is it on fire? Again, the hard part of these is just getting the dumb things written out. In the real world, if you ever were doing a question like this in the real world, you're done right now because you just type that into Desmos or go to CY Math or Wolfram Alpha and just say, you know, tell me the answer to it. Let's see if this is doable. Like, is this a doable integral or is this terrible? Actually, don't know. I just made this problem up right before class. Remember, we can move any constants outside if that's of any benefit to us, and then that leaves an x behind. And then let's subtract all of this. So let's see, there's a minus x squared, and then there's a 2x minus a minus 6x. That's 2x plus 6x, that's 8x. And then there's a 4 minus 11. 4 minus 11 is negative 7. Oh yeah, this is doable. That's easy. It would not be doable because it's junk times junk, but remember I can distribute that in there. So yeah, this one's doable. This is a good example of maybe a good test question or something like that then. Because that only requires the power rule for us to be able to take its integral. So I'm now taking the integral. So the integral sign disappears. That becomes x to the 4th over 4. This becomes x cubed over 3. And that becomes 7x squared over 2. So none of those simplified very much, but I've just got to evaluate that at 7 and evaluate that at 1. And then I will know the volume of that cool disc-like shape. Quickly do that. So I'm going to say 2 pi times, and I'm just going to stick 7 into that whole mess, negative 0.25 times 7 raised to the 4th plus 8 divided by 3 times 7 raised to the 3rd minus 7 halves times 7 raised to the 2nd. Dun, 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 dun. 2 pi times 7 raised to the 4th plus 8 divided by 3 times 7 raised to the 3rd minus 7 halves times 7 raised to the 2nd. Dun, 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 dun. 2 pi times 7 raised to the 4th plus 8 divided by 3 times 7 raised to the 2nd. And I got, and maybe I'll change this in just a minute. Well, I'll change it right now. I'm going to turn that to a fraction. I got 142.91666666, but let's change it to a fraction. Let's get it exactly right, just because it's cool. I got 1715 over 12. Now, if I go back and redo that with 1 in it, hoping that I don't type something in wrong. Double checking, plus 8/3 times minus, I think that's right. It's always minus, but I got a negative 13/12, so I'm actually adding them. So 17/15/12 minus negative 13/12. Maybe we'll get lucky and that'll come out a whole number. It did, 144. Oh my gosh, that's really cool. So that came out 2 pi times 144, which is obviously 288 pi cubic units or cubic centimeters or whatever. I'll just leave it alone since I ran out of space. Amazing. We actually got it exactly right. That is unbelievable. That is just cool that it could even be done. Talk to me. How much pain are you in right now? It's painful.
I think the math makes sense to me. I'm just like failing to see like how whoever created this method saw that the cylinder would equal that weird little volume.
Isn't that weird?
Like, how did they come up with that?
Yeah, isn't that a brilliant idea? It's crazy because you're right. One part of this is just learning how to do it, but another part is somebody figured this out. Somebody thought this up. Insane. Just to give you another second to process, I'm gonna do one other thing here real quick. Because a big part of this that I think is hard is just picturing even what this thing is. So just going to take a stab at that really quick. So do you see what this shape is? So it kind of looks like a bowl on the outside. Does it make sense? The outside of the parabola defines it. So if you saw it sitting there, you'd go, oh, look at that bowl. That's really cool. It's a bowl. It looks an awful like a cereal bowl. Except when you look down inside it, you'd see that, well, actually the inside is a cone, and oh, there's even a hole out the bottom of it. So this is not a bowl. There's a hole. This is going to leak out the bottom. So
it's a bunt pan.
What is it?
A bunt cake pan.
Yeah, similar to a bunt cake pan. It's a lot closer to that than anything else. You're exactly right. Maybe this doesn't even help down here. Yeah, so it does look an awful lot like a bunt cake pan. I think that's about the best you could do. You're right. So it's just cool that it could be done this way. Now, these methods are all very hard to conceptualize. It'd be one thing if I'm sitting here cheating using a drawing program. It'd be really cool if I found a 3D program. I kind of showed you a little bit in AutoCAD the other day where you could actually, spin it around and look at it and conceptualize it and even draw draw it in a see-through. It's actually like 3D, but it's see-through, and you have the shell sitting inside it, and you could even slide it around and move it and watch it get smaller and bigger. That would be really cool. And that would really help to visualize it and so forth. But what worries me on a test is, if I just say, hey, find the volume of this, it could be a lot of different methods, and sometimes one is different than the other. And so on a test, what I'm going to do for sure is I'll say use cylindrical shells on this problem, either because I just want to see you demonstrate you can do it, or because I know that that's easier in this case. So I'm not on a test, because we're not spending that much time at this, going to leave you to just figure it out which method works on your own, because it takes a lot of practice to do that.
So the cylindrical shell method, that's basically treating the cylinder as if it's a rectangle.
Yeah, basically we're finding the volume of that shell. It's easier to find the volume of the shell. I don't know, is easier the right way? We're saying it's easier to find it by thinking of it as a rectangle opened up rather than two cylinders that I'm going to subtract. Maybe it is. I would assume it is easier, although off the top of my head, I can't remember if that's the case or not.
Yeah. Instead of having to subtract one from the other. So could we use this on some of the problems from yesterday?
Yeah, that's right.
I assume.
Yep. So this could set up an integral that's easier to take, or it could be harder to take. The ones that are kind of fun are ones where you can do it both ways. This particular problem we just did, you couldn't do with washers. So we can't do it both ways because of that problem that I mentioned here where that bottom one doesn't work. But it's cool if you could do it both the same, just because then you can get the same answer both ways and kind of know you're doing it right, or maybe you don't, and then you know something's not quite right. So let's try let's make something up here. How much time do we have? We don't have a lot of time. Let's see, are we? So let's make up a fairly simple shape, but let's also do something your book assignment does that's a little meaner. Let's take a super simple parabola, like y equals x squared. So let's define our shape by y equals x squared, and let's do it with y equals 5. So if I go up here to 5, then I'm sort of saying, okay, cool, let's chop this thing off. And so we got this shape right here. Now, if I was to spin that around the y-axis, that's like right on top of itself. Does that make sense? But something else you can do that takes a little bit more creativity, and you have these in your assignment, is, so we're talking about that area right there, but do you have to just spin it around the x or the y-axis? What if we sent it around, let's see, there's 5. What if we sent it around the line x equals 8? What would that look like? Give you a second to process this. Would you agree that, copy, paste, it's about right there. Can you picture that shape? If I spun that around, what are you seeing?
It's like a bagel with a big center.
That's exactly what this is. It's half a bagel. It's a bagel cut in half. Again, hard to conceptualize 3D. So, you know, it has a practical element to it. Half a donut. Could you set this up with cylindrical shells? Let's see. I'm going to try to draw a picture of it. So I need, here's one side of it, and that would be also over here in the same exact location. So there's its height, and I need that thing to spin around. Probably I should just get rid of that red line. So there's my cylindrical shell. Remember though, our y-axis was actually over there, given what our equations are. So isn't our, let's do this in a different color. Let's just try to reason it out rather than use a formula. Isn't our height equal to, again, it's kind of top minus bottom. So isn't it the y value of the line minus the y value of the parabola? So that'd be 5 for the y value of the line and x squared for the y value of the parabola. Isn't that right? And the thickness of our slice is a little bit of x, since that's parallel to the x-axis. But our radius is a little trickier in this case. What's our radius? Well, if it's spinning around the line x equals 8, isn't that our radius? So how would you write that down? Like, what is that? And remember that, you know, that shape has got to change. It's going to move locations, right? It's going to move left and right and so forth. Well, we know from here to here is 8, right? That stays the same. How far is it from here to here? Isn't that the x coordinate of the parabola? So based on the picture, then, isn't the x coordinate of the parabola plus r always have to be equal to 8? Is that true? Or I could say 8 minus the x coordinate of the parabola equals r. Is that going to work when the shell is over there? 8 minus the x coordinate? Like when that's over there at, let's see, we said that's not a very nice choice of numbers. Y is 4, or y is 5. Like, let's say when this is out here at like -2. Well, let's see, that'd be 8 minus a -2, that'd be 10. Hey, I guess it does work. So it'd be 8 plus 2 would be 10, so the radius is 10. I think that is working. So let's see, the volume, I'm just thinking out loud here with you slowly. The volume of kind of my box is the thickness of my box times the height of my box times the circumference. So for us, the height we said was 5 minus x squared. And the radius is 8 minus the x. Two times pi times radius. So there's the radius, the x coordinate of the parabola. Okay, that's all x's. That's good. So the key to the calculus side of this is I have to let this slide around while x is everywhere x needs to be. I need to let x change, and I've got to add them all up while x is changing. And, you know, by the way, this x is also the x of the parabola. So let's see. So to write this in maybe a more normal kind of a way, I need to add them all. I am interested that you notice that we're really just using that same formula. If you want to write that formula down and just use it, you can. However, you know, this worked when we went around. Looks like I said x-axis, but that should have been y. Didn't we just go around the y-axis? Yes. That was an important mistake. So we're not going around the y-axis though. We're going around some other point. And so this x right here, this x right here was that was the radius effectively. Well, our radius was a little more complicated than that. Our radius was Our radius was 8 minus x, if you will. In a sense, that's our radius. So if I add them all, I've got some constants. I've got 2 pi, I'll leave that outside. And then I've got 5 minus x squared, which is multiplied by 8 minus x. And then there's a dx. That's doable because I can multiply it out. What x's, for what x's does this exist? This is not easy, not obvious. Well, this was a y coordinate of 5. And in the parabola, if I put 5 in there, I'm going to have to take the square root of that. So this is actually the square root of 5, and this would be negative the square root of 5. So this exists from square root of 5 to negative square root of 5. So me picking the top of that being y is 5 wasn't very nice. I could have said, let's take it up to 9, and then the square root of 9 would have been 3. But that's okay. This isn't terrible. So back here we had the volume of really one box with x for the location as a variable, and it was where is this particular shell that we're talking about right now? Well, we put an x in there. When we jump down to the next level, we say, great, let's multiply all those out, but let's add them all. Let's add every single one of them while x works its way from negative square root 5 to positive square root 5. And this is good practice, so let's do it. We can take this integral. So let's see, 5 times 4, 5 times 8 is 40. 5 times x is 5 times x. There's no such thing as math with letters. Negative x squared times 8 is negative x squared times 8. And x squared times x is 3x's. So, hey, good. I don't have product rule. I got this down to where all I need is power rule. So I can do this. This is a little time consuming on a test. Again, on a test, I might say just write out the integral and you're done. Although that isn't very satisfying. Or I might say use Desmos to cheat and answer it. Don't do everything we're doing here in orange. The integral is now taken, so there's no integral sign. 40 grows an x. The 5 grows another x. The 8 grows another x, and the x cubed grows another x to the 4th. Hoping you're good at the power rule. And now if I evaluate that at the square root of 5 and at the negative the square root of 5, and that's a terrifyingly, that's a disaster. I mean, there's still an exact answer to this. It's going to have square roots and so forth. It's going to be really ugly looking. So, I find myself not wanting to know what it is. I find myself regretting not thinking a little more about y equals 5 and, not picking 9, because then this would have been 3 to negative 3 and I would have had fractional type answers. So this is going to come out really messy. I'm just going to give an approximate answer to this. I'm also thinking about symmetry. Would this be possible just to go from 5 to 0 and then double it? Because that would save me some time, wouldn't it? I'm not sure, so I'm going to do it sort of the long way, and then we'll see. Minus 2.5. Minus 8/3. Minus 1/4 times so because I am wimping out, I'm going to say 2 pi times, and when I stuck in the square root of 5, I got 40.878. The question is, when I say minus, am I going to get another of the same thing, like get 40.878 again? I'm not sure. I'm guessing no, but I'm not sure. If you think about what that negative sign is doing, just thinking out loud, because this is good for your algebra knowledge, the negative is going to change this sign, but it's not going to change this one because it's a negative squared. So that one's going to stay minus 5/2 times whatever the answer is. And this one, it will change. That'll turn into a plus sign, but this one, it won't change. So I didn't get the same thing. So symmetry would not have worked. I got negative 78.378. So if I subtract those two, I get 119. If I multiply it by 2, I get 238. Again, it's kind of stupid to say this is approximately equal to 238.5 pi. So I'm just going to say times pi. I got 749.3, close enough. Again, cubic inches, cubic centimeters, something like that. It'd be a catastrophe to be asked to answer this exactly correct, given that it had a square root in it. Should be capable of it, but So you see what I mean? Like you could miss this problem just because of the nastiness of even plugging those ridiculous expressions in. And I'm not 100% sure that I didn't screw that up too, but I think I went slowly enough that I didn't. Again, how could I check my work? I could go back to that statement right there and type that in my calculator and just cheat and answer it, which I probably will do before I kind of post these notes. But this should hurt your brain. I mean, collectively, when you kind of, you know, we can rotate around the x-axis, we can rotate around the y-axis. We have a disc or a shell or a washer. And this last problem, we even rotated around not even the x or the y-axis. That's nasty too. Again, I think that around this axis, around a non-x or y axis, I think that's fine for a homework assignment. There's 3 or 4 questions in your homework assignment that ask you to do that, but you're not going to see that on the test. I would change this problem to just go around the x or the y axis and keep it a little simpler than that. Because in the real world, I can see somebody saying, hey, is there a way to find the volume of this bagel? Maybe it's made out of metal, so it's more interesting. And as I said, it'd be way easier to dunk it in water than actually do all of this calculus. But if you had some reason to do this, you would be sticking it on the graph paper yourself, and you would never stick it on the graph paper to rotate around a weird axis. You'd stick it on there to rotate around the y-axis or the x-axis. So you're not going to see that on the test, and you won't see it in the review for the test either. But it's amazing that you can actually do it. I mean, isn't that cool? So what we're really looking at here is anything in life that has kind of rotational symmetry to it. If it has any kind of rotational symmetry, whether it's hollow or solid, calculus allows you to figure out volumes of things that there is no formula for. That's kind of the idea. I'll leave you with this. If you put any time into this, but just as an example of something that's a little bit more practical than this, if we took a donut now, as a donut, again, that just seems like, you know, nerds at the bakery. Like, why would you find the volume of a donut? But what is that shape? What is that shape in our culture that's more of a mechanical? Like, have you seen that shape? That's kind of a really lousy drawing of it, but.
Is this the washer again?
Yes, except for it's round. Like what we did before was
a tire.
Washer, but yeah, like a tire. A tire is another example. What else?
An O-ring.
Yeah, little rubber O-rings are used to seal your. There's like 20
or a seal.
Yeah, seals. Anytime you have two metal pipes that come together and water's going through them at high pressure and you don't want them to leak, you put a little seal like that in there, a little O-ring like that in there. So yeah, and you know, even a ring, you know, like, ugh, I can't get my wedding ring off. My finger's too fat. Wedding rings are kind of shaped like this a little bit too. Mine's a little bit flatter, but you know, as an example of me wanting to ruin your life, there's examples of shapes like this that have a rotational symmetry everywhere. There's all kinds of parts on this pencil that have a rotational symmetry. That yellow shaft right there, this shape on the end that, you know, is kind of a conish sort of a shape. I mean, all of those have a rotational symmetry to them. But this donut, couldn't that donut be conceptualized as, well, it has a couple of radiuses. There's like the radius of the circular end, but then isn't there also this kind of capital radius to the center around which it rotates? That's the only 2 dimensions it takes to define a donut. And so I'm just kind of wondering out loud, if you stuck it on the x-axis over here, you stuck a circle on the x-axis and you located it a distance of capital R away for that radius, and this distance right here was the radius of the circle itself, and then you sent it around the y-axis, what would the formula for that be? What I'm going to do quickly, and I'll come back to this in a second, is in the real world, what do you do if you want to know the formula to that? Well, you just go to Google, cheat, do it. Anybody know what this is called in the real world, the mathematical name for this? It's actually not a donut. Does anybody know what it is?
Taurus.
Yeah. Torus. Notice, isn't this cool? This person has a, like even has the formula built in. This is kind of this what algebra looks like in the real world. You just enter in the value for your major radius. So I guess they're calling capital R the major radius. So they're labeling this like I just did a second ago, fortunately. And R is the minor radius. And so there's the formula right there. Pi R squared. So it's like the circle times 2 pi R. Let's make sure that that's the, looks like that's it. How do you calculate the volume of a donut? Yeah, it's all the same formula. So there it is, pi R squared. So I guess that'd be 2 pi squared R or something like that. I'm writing it down. 2 pi squared R, little r squared. I got that backwards. The little r is squared, but the big R is not. So my point is, this shape, this particular shape exists in culture enough in, popular culture with respect to, a physical donut that you would eat. But also this is a lot of different shapes. This is used a lot, wheels and all kinds of shapes, O-rings and metal rings, and like your key ring is kind of shaped in that same kind of fashion. So look, somebody's found an algebra formula for it. That makes sense, but it came from calculus. The question is, could you pull the same thing off?
Well, even without the calculus, it kind of makes intuitive sense as if you're using the area of a circle as the circumference of this torus.
Describe that a little bit.
Well, when you think of the torus, it's almost like instead of having just a flat line as the circumference around it, you're using a 2D circular shape, which is the 2 pi R.
Yeah. If you think about the way that formula was written a minute ago, isn't the cross-sectional area of the donut just a circle? And so that's pi R squared. And so then if you send it around a circle, just like a minute ago, didn't we take that cylinder and kind of cut it and open it up? If you took this shape here and you cut it and opened it up, wouldn't it just be like a long tube? So it'd be, if it was a long tube, wouldn't it be the area of that end times however long that is? But how long would that be? Well, wouldn't it be the circumference of, and I think this is what Felix was saying, wouldn't it be the circumference of that shape right there, which is 2 times pi times radius? So that's A. The volume is A times that L. That's the way that formula was written out a minute ago. That's exactly true. But the key is it's the circumference of the center line of the donut, not the outer or the inner one. It's the center line. So you're right. Like, it doesn't even take calculus to conceptualize that formula would work. So the extra credit is knowing the formula, just stealing it offline, or even using logic. Could you pull the same thing off? I will tell you this as well. I wonder if you could still come up with the equation of that circle right there. Well, circles are x squared plus y squared equals r squared. But this one has been slid right by a distance of capital R. How do you modify that equation to slide it right?
Is it minus the capital R?
That's exactly right. And because it's in the x direction, so that would be the equation of that circle. So the question is, could you take that and spin it around the y-axis and maybe use discs, maybe use shells? I'm not sure to do it. I know for sure I would tend to want to just take the top half of this and send it around and then double my answer, so that you're kind of doing that bagel problem we did a second ago. But again, this is where, to the point that I started the class with, I got to shut up, but this is what calculus really does. People are seldom, if you're honest about it, people are seldom, ever coming up with a problem like this. And the reason is because where in life would you actually have this shape be a genuine parabola? That's the problem. Like in real life, that probably would be a circle. Well, if it's a circle, then, well, we have an algebra formula for it. Like, it actually, if it exists out there, then somebody's made an algebra formula using calculus, and then nobody even knows it's calculus. You see what I'm saying? Most of us would have went and looked this formula up online and just went, oh, some genius. But no, you are the genius now. That's the point of taking this class. Like, somebody's got to figure this stuff out in the first place. And obviously just learning how to think is the more important part here. But the largest use calculus has is creating algebra formulas. So we have a ton of them in my engineering classes I teach that came from calculus. And just being the kind of person I am, that bugged me like, where did this come from? How does this work? And where did this formula come from? And I'm always bothered by that. And oftentimes calculus is involved in creating that. So, it gives me a sense of power over it. Like, I understand the problem. And if somebody throws me some little curve ball, like, hey, let's rotate it around x equals 8 instead of around the y-axis, because I can conceptualize the problem, then I can, still get it right. But this stuff is hard. This is a challenge. And fortunately, tomorrow we're going to do a project that's related to this extra credit torus problem. It's not quite the same. And that'll give you time in class to ask me questions about the assignment. It'll give you time to work on the project. And so we don't need to learn anything new tomorrow. But that's the plan for that. And so, as always, stay after if you have any immediate concerns. You do owe me the second quiz by tonight. So a few of you have sent me texts and emails about, hey, I got this for number 7. Is this right? Stay after and ask me those questions. That's good stuff, because you owe me that tonight, and then I'll grade that.
Hey, Doug, I actually do have a question on the quiz.
Yeah.
This is for 2A.
Sounds good. I'm